My name is Kang from the Endurance Life Group in the University of Illinois. We use the blue waters for first principle study of the voltage-induced switching and optical properties and the heat capacity of the antiferromagnetic metals. We are interested in the magnetic materials, which is contain these magnetic moments. Magnetic moments is the consist of the spin angular momentum and the orbital angular momentums, and it have a strong two different direction, which is the upspin and the downspins. And the spin direction is controlled by the external stimulations, such as the electric field or magnetic field or the electric current. And because we have up and down spins, so this is corresponding to the binary numbers, so we can store the information using the magnetic materials. Famous example is the hard drivers. If we have a parallel spin in the materials, then we call this the ferromagnetic materials. And if we have an alternative spin direction configuration, then we call it antiferromagnetic materials. And we are interested in the antiferromagnetic materials because it is very robust to the external magnetic field. And this showing the faster dynamics than the ferromagnetic case. It's about the terahertz response. And it does not generate any stray field outside the materials, so it does not affect any material nearby. We have two different projects with the blue waters. First one is the voltage-induced switching of antiferromagnetic semi-metals. This project, we interested in the changing of the order parameter, which is the spin configuration. And then we cause the electronic band structure opening after that we change the spin orientation. And this is first studied by the model Hamiltonian study, and then we confirm it by using the density functional theory study to this one of the real antiferromagnetic materials. And we will visit the second project later on. So we're interested in the antiferromagnetic semi-metals. This material has antiferromagnetic configuration, and it also has this Dirac semi-metal electronic structures. And this material have a PT symmetry, which is the inversion and the time reversal symmetry with the non-symmetric crystal symmetry. And under the certain conditions, then when we change the orientation of the spin configuration, then we can also cause the band gap opening of the electronic band structure. So because of the change of the band structure, we kind of expect different electronic transport properties from these materials. So we call this kind of phenomena as the metal insulator transitions. And this has two conditions. First one is you should have a PT symmetry, which is the inversion and the time reversal. And another condition is the additional symmetry, which can protect this crushing of the band structure. And when we switching the spin like this, then this symmetry is broken, then we can cause this band gap opening in the electronic band structure. So for example, if we have a non-symmetric glide reflection symmetry as this additional symmetry, then we have two operations, which is the mirror operation and the translation operation. So let's say we have a x direction spin directions. Then the initial configuration is darker colors. Then after we apply the mirror and the translation operation, then we can say that the initial configuration is the same as the final configuration. So we can say symmetry is preserved, so we can protect this crossing of the band. And for the reorientation of the spin configuration case along the y directions, then the mirror operation is changed. So after the translation operation, we got the different initial and final structures. So we can say this is the broken symmetries. So now we does not have this additional symmetry, so we can cause the band gap opening in the electronic band structure. So this study is originally starting from this Gilbert group in the ECE in the University of Illinois. And they starting to study with this simple model by the model Hamiltonian. And then they do see the band structure change in terms of the Néel vector change. And then we start to find the same material which can satisfy this condition in the real material. And we found that this orthorhombic copper manganese arsenide have that certain symmetries. And we found that in terms of the Néel vectors, we can find the band gap opening and the closing in terms of these Néel vectors. And we need some kind of the accurate resolution in terms of this band structure. It's about the 40 millielectron volt. So we draw the very precise 2D case space with the precise energy scheme through the three-dimensional plots, and we do see the band gap opening at here. So we know the band structure will be changed in terms of the Néel vectors. So we also we kind of proposed the new switching process. So by changing the chemical potentials, because these two states have a different band structures, so this changing the chemical potential also causes the change of this anisotropy free energy change. So if we change the chemical potential from the 0, then initially it was insulating, and then when we decrease it, then it changes the anisotropy energy, so it transitions to the semi-metallic states. So this kind of calculation required a very high accurate calculation on the energy and the Fermi level evaluations. So we increased the K point up to the 2020 by 4040 by 22 to the sampling the Bruyère zones. And this calculation also includes the non-collinear magnetism with the spin-orbit coupling effect. So this calculation kind of demand the Blue Water's resources to calculate the accurate results. And let's move on to the second project, which is about the optical and thermal properties of antiferromagnetic materials, iron torogenite. And we studied about the linear magneto-optic effect from the antiferromagnetic materials under the strong external magnetic field. And also we checked the relationship between the quadratic magneto-optic effect with the heat capacities. So for the simple background about the linear magneto-optic effect, so to date, people are interested in the ferromagnetic materials. So ferromagnetic materials have a net magnetization. And when we shine on the light on this ferromagnetic material, then the polarization of the reflected light is changed. So we can read the magnetic information by detecting this polarization change. But for the antiferromagnetic materials, we don't really have any net magnetization. So we cannot get any magnetic information using the optics. So we wanted to utilize this optical detection because optics are very simple and fast response. So we proposed two different methods. The first one is the linear magneto-optic effect under the external magnetic field. So we applied a very strong external magnetic field and then making it the tilting, and then generate the net magnetization like ferromagnetic case, and then to see some signals from the materials. And another one is the quadratic mode. Quadratic mode is the second order response. So this is depending on the sublattice magnetization. So even though we don't really have a net magnetization, we can detect some kind of the second order magneto-optic response from the antiferromagnetic materials. And we see some kind of the temperature dependent of these quadratic mode signals. So here is the ground state calculation. So it's showing the reasonable close to the experimental measurement in terms of the lattice parameter and the magnetic moment. And we also calculate the basic optics for the reflectivities, and it's also showing the close results to the experimental measurement. And we also calculate the electronic band structure and the phonon band structures. And electronic band structure, based on the electronic band structure, we can calculate the excitation of the electrons. So we can calculate this dielectric function, and also the linear magneto-optic effect signals. And using this electronic density of states, we can calculate the electronic heat capacity. And based on the phonon band structure, we can calculate the phonon heat capacity. So first one is about the linear magneto-optic effect study. So we applied a strong external magnetic field, and overall structure are start to tilting. And we calculate the spectral result based on this dielectric function from the band structure. Then we can get some signals. This yellowish line region is about the visible light region, and we got the certain signals. And we asked our experimental colleague to measure the co-rotation, and they only have this 1.56 electron volt lasers, and they do see some signals, and this is pretty well agreement with our predictions. And based on our spectral result, we can propose that for the electricity is about 3.3 electron volt, and the rotation is about 2.9, can get maximize the signals from that. So we kind of giving a guidance to the experimentalists to choose the wavelengths to maximize the MOC signals from the antiferromagnetic materials. And another one is the quadratic MOC study. So our colleague, experimental collaborator, measured quadratic MOC in terms of change as the temperature increases, and they do see some peaks near the Néel temperatures. And we thought that this is the temperature-dependent properties, so we want to study about the heat capacity of the materials. And what they can measure is the total heat capacity of the materials, and what we can calculate is the electronic contribution and the phonon contribution. So by subtracting this electronic and phonon from the total heat capacity, then we can extract this magnetic heat capacity contribution. And by plotting with this optical response, that we do see the relationship between this magnetic heat capacity and the optical response. So we can say that the quadratic MOC response is the dominantly related to the magnetic heat capacity. For this calculation, we implement the phonon calculation with this 3x3x2 supercells. Still, we need to include this magnetism for the phonon calculation. So we using the non-collinear magnetism with the spin-orbit coupling, using this huge supercells. And also we need to calculate the 6 displacement calculation for the whole phonon Q-space calculation. So this calculation required to the large resources of the calculation, so we're using the blue waters to study this project. So our conclusion. So we study about the semi-metal interlayer transition and propose the voltage-induced switching in the antiferromagnetic semi-metals. And also we predict some kind of linear magneto-optic effect under the strong external magnetic field and confirmed by the experiments. And also we found some relationship between the quadratic magneto-optic effect with the magnetic heat capacity. And this project is funded by the IMERSAC and also supported by the Blue Waters allocations. Thank you.